gentlemen, this is Mr. Green. This is another in my series of lessons for AP Statistics. Now, just a couple of things. This week, I have to go to Dallas to be with the other teachers for professional development. So I will not have a class connect this week. So this recording is going to double as both things, both as the Unit 7 Lesson 1, Study 1, and also the class connect for this week. So I want to make certain I cover a couple of things there. Due dates. We are going to have 28 days to get things done. So you want to make certain you get things done before we reach that 28 day. Do not let things stay as a zero for very long because then they become locked in. We don't want that happening. Okay. We are taking up the concept of confidence ranges. This is where we start to develop a range of values and we say we have a confidence or some degree that we believe the mean of the population will be within that number. This is really good for developing numbers that you can look at and say, okay, I believe the number will be between this number and this number, and I believe it to 90% possibility. That gives you a really good feeling about the range of numbers you get, and as long as the number range is significant, it makes sense. Just as long as it's not something that's so huge that you can't deal with it. It really helps a lot. I think the best way to see this is to actually work some problems and see how they're worked. So here I've got a problem. It says the following airborne times in minutes for United Airlines Flight 448 from Albuquerque to Denver. Randomly selected days are given below. What are they saying? They mean they selected the amount of time that the plane was in the air for this flight 448 Albuquerque to Denver. Okay? Okay? So they want you to compute and interpret a 90% confidence interval for the mean airborne time for flight 448. Well, first of all, a couple of things. One of all, first, we need to make certain that these are simple random samples. Okay, we got to assume that that's true. It's just not 10 specific times. It's randomly sampled over a period of time to give us, a simple random sample so that we can say that we've got normality, things like that. Um, so let's look at this. If we take our calculator, which I don't have running right at the moment, so hang on a second while I start my calculator. Okay, got my calculator running now. So let's bring that calculator up. And what I'm going to do is, I don't want to do that first. First thing I'm going to do is I'm going to go into Stat and Edit, and I'm going to add those times right here in L1. You can see I've just added them in. Okay, nothing special, just keyed the numbers in there to L1. I'm going to press Stat, not second Stat, just Stat, and I'm going to calculate, and I want to calculate the one variable statistics. Why am I doing that? Because I want to get the X bar and the sigma of X. Okay, so what do I get there? I get an X bar of 54.2. And I get a sigma of 3.6, 3.7. Is that what I had there? 3.7, yes. Okay. So if I'm computing a 90% confidence error, what you can do, remember that our confidence range is going to be X bar plus or minus my confidence number, my Z star, times my sigma divided by my square root of n. So if I do that on my calculator here, okay, go away. Thank you. 54.2 plus parenthesis 1.645 is the 90% confidence error times 3.7 divided by second square root of 10 parenthesis, hit enter, and I get a 56.9 1 as my upper end. I'm going to pull a couple of tricks here. I'm going to subtract the mean, 54.2. So then I'm back to what just that other part of the equation there is. And then I'm going to say, I'm going to take 54.2, the mean again, minus what was in the answer. And I will get my lower end, 52.3. There's my range. Now, what does that mean? That means that the airplane is taking 90% of the time, it's taking between 52.3 and 56.1 minutes to fly from Albuquerque to Denver. And I'm 90% confident that it's going to take that long. So, based upon that interval, if it's scheduled to depart at 10 a.m., what would you recommend the published arrival time be? Well, you know what? One of the issues here is you want to not fool people. Airlines are measured based upon how many times they arrive on time and things like that. Let's use the high end number. So we would say that it arrives at 10:56 is what I would say is the arrival time. And that's, if you look at the answers that I've got published here, they're saying that it's a simple random, given simple random sample of flights. It's approximately just normal. They actually did a box plot here to prove that it was normal. We didn't know the sigma, and so what I did there is we found the sigma by using the one variable statistics, and they give a confidence interval of 52.1 to 56.3. And what we have? 52.3 to 56.1. Sounds like one of us is dyslexic a little bit here. So we're just going to leave it at that. So just like I was saying, arrival time or not, I would use an upper bound number, and I would use that 57.7 or 10.57 as the minutes. Okay? Okay, let's look at another problem, see what we can do here. A triathlon. Well, I assume some people in our group could actually compete in triathlons. They're swimming, cycling, running, right? And they're an amateur sporting event. A research study reports that the maximum heart rates in beats per minute for 9 randomly selected triathletes were as follows. And this, in case you can't read it, this is the X bar and this is the S bar or sigma. Okay? So assuming the heart rate distribution for each interval, for each event is approximately normal, they want a 95% confidence interval for true mean heart rate of the triathletes for each event. So that means we need to find 3 confidence intervals. Okay? So what's our formula again? X bar plus or minus, and it'll be Z star times sigma divided by square root of n. Okay, now most of these are known figures, so it's not going to be hard to do here. Let's see here. For the Z star, we're going to be using 1.96 because we're using a 95% confidence interval. So it's going to be 1.96 for Z star, right? We got our sigmas are in the table. Our n star, our n in this situation is 9. And so we want to construct these confidence intervals. Okay, so what are we going to say? We're going to start by just bringing up our calculator. Clear. It's going to be 188 plus parenthesis 1.96 times 7.2 divided by second square root of 9, close parenthesis, and we get a value of 1.92. Okay? I need to write these down. 192.7 or 193. That's going to be the high end number there. Okay? So if I want to find the low end number, I'm going to subtract from that the 188. Take 188 minus what was in the answer, and I get 183. That's for swimming. Okay? So let's do biking now. Now, yeah, these numbers are all changing. Okay, 186 plus parenthesis 0.96 times 8.5 divided by 3. Square root of 9 is 3. I just why put square root of 3, square root of 9 if you know it's going to be 3. Okay, that one we get a 192. And I'm going to once again subtract the 186 from it. Take 186 subtracting what was in the answer, and I get the value for the low end of 180. Okay? Okay, last one, running. So we're going to take 194 plus parenthesis 1.96 times 7.8 divided by 3, and we wind up with a 199. Okay? And we take subtracting 194, taking 194 minus what was in the answer, and we get a 189. Okay, I calculated the 95% confidence level. What is this meaning? That means that at the end of the swimming, a randomly selected runner, we would say we have a 95% confidence level that his heart rate is going to be between 183 and 193. At the end of biking, his heart rate would be between 180 and 192, and after the running, it would be between 189 and 199. Okay. Based upon the computed confidence intervals, do you think there's an evidence that the mean maximum heart rate is higher for running than it is for the other two events? Well, you know what? It appears to be a little bit higher, but we're using a really small random sample here, okay? And so, to be honest with you, I'd say it's not as significant as it looks, okay? Let's see here. What did they come up with? They came up with 182. Well, I said 183. They said 180, 193. I got 193. 180 and 180, 192. 180 and 192. And 189 and 199. Yep. Cool. Now, what they're saying here, since all three intervals overlap each other, not significant evidence to conclude the mean maximum heart rate is higher than the other two events. What they're trying to point out to you here is, since there's enough overlap here, you could have swimming and biking be higher than the running one. So you can't really say that it is 95% of the time, you can't really say that it's going to be happening that this one is highest. But you can look at this and say, yeah, it's a little bit higher, but it's not significant enough that we would want to deal with it that way. Okay? Now I'm sure you're asking me, why are your numbers slightly different than the numbers I'm getting on this answer sheet? It's different in the way that rounding is done and the way the calculators are done. This was an old worksheet I pulled these off of, so maybe they were doing it slightly differently than I'm doing it here. But we're getting the right numbers in the right area there. Okay, here's a interesting little one. It says an article in the Journal of Irreproducible Results. Yes, there really is a journal by that name. It's a spoof of a technical journal. It predicted dire consequences resulting from a national-wide buildup of National Geographic magazines. Since subscriptions are increasing and no one ever throws issues away, the key to the analysis is the weight of an issue of a magazine. Suppose you were assigned the task of estimating the average weight of an issue of National Geographic. How many issues would you have to sample to estimate the average weight to within 1 ounce, or I'm sorry, to within a tenth of an ounce with a 95% confidence error? Let's say that we know that sigma is 1 ounce. Well, we know that what we're looking for here is zero point 0.1 to be equal to, we're using a 95% confidence error, so it's going to be 1.96 times with a 1 ounce variance there. Okay, that's, sigma's 1 ounce there. And we're going to take the square root of n. That's what we're looking to get, right? So all we have to do is actually work this out for n. So I'm going to multiply it and then divide by that. So I'm going to bring up my calculator here, move it over so I can actually see what I'm doing here. I'm going to take 1.96 divided by 0.1, and then I'm going to square that number. And I wind up with 384. Well, we can't do a partial one. So I'm saying that n needs to be 385 magazines. Let me see what they came up with an answer. Exactly right. 385 magazines. All I did there was I took 1.96 times 1 divided by 0.1, and then I squared that number, and that's what n is going to be equal to. That was a little bit of algebra work that I did there in my head. Okay? Okay, well, just to let you know, that's how you work some of these problems. So hopefully it'll help you. What we are looking at is we're looking at the meaning of a confidence error. Okay? Confidence interval. We're trying to get a good handle on that. These are some of the other topics we're going to cover in Unit 7, so we'll get to some of those a little bit later on. My secret word for today is plywood. So if you're watching this Class Connect or this as your lesson video, either way works for this week. You can do it both ways. Send me a K-mail, plywood, and that will give you credit for having watched this, and we'll be in good shape. I do appreciate the fact that you guys send me the fact you're in AP Statistics when you send questions. It really helps because I'm doing so many different classes. Keeping track of everybody sometimes is a little bit difficult. I do appreciate it though. Anyway, I'll look forward to seeing you next time. Bye.